Welcome to the Explainer. We're jumping right into something really foundational today. If you're a focused learner wanting to, really master how our digital world actually remembers, organizes, and utilizes information, well, you're definitely in the right place. We're going to take a bottom-up journey together. We're starting with the absolute most basic atomic units of digital storage, literal raw data, and working our way all the way up to the structural rules and languages that run modern database systems.
Here is our roadmap for today. First up, data, information, and knowledge. Second, we'll look at early file system flaws. Third, SQL basics, specifically focusing on DDL versus DML. And finally, number 4, understanding primary keys.
All right, let's dive into Section 1, data, information, and knowledge. Let's get these fundamental units defined right off the bat. Now look at this. This is kind of the aha moment of database theory. Over there on the left, you've got your raw data. Literally just lines of zeros and ones. On its own, totally meaningless to you and me. But when we run it through a system, we get what's in the middle, information. It's interpreted, so it looks like those bar charts and trend lines. Make sense? And then finally, on the right, you get the human element. That's the gears turning in someone's mind, taking that information, combining it with their own past experience, and actually making a decision. That is knowledge. It's that whole journey from a raw random fact to a genuinely actionable insight.
Let's lock these definitions down. Data is just raw facts about people, objects, or events. Information is that same data, but presented in a way we can actually interpret. And knowledge? That's what gives us the insights we need to take action. But okay, here's a crucial takeaway that actually surprises a lot of people. Databases and files, they don't actually store information. No way, they only store data. It's the programs, the specific queries running on top of them that do the heavy lifting to convert those raw facts into the information we can actually use. To put all this into perspective, just think about the high-stakes stuff running our world literally right now. In banking, databases are managing customer accounts, loans, credit cards, all in real time. Or universities, keeping track of every single registration and grade. Even the navigation system on your phone relies on massive document and location databases to map out your exact route. And online retailers, they track every single order. Every single one of these scenarios relies on complex SQL queries, filtering mountains of raw data to give you split-second, actionable knowledge.
Moving on to Section 2, early file system flaws.
So, getting to this level of seamless, everyday organization, well, it wasn't easy. Let's talk about the historical chaos that kind of forced modern databases to be invented. In the early days, applications were built straight on top of very basic file systems. And man, this created massive flaws. First off, data redundancy and inconsistency. You had information duplicated across a bunch of different files in totally different formats. Think about it. If a customer changed their address, you just had to cross your fingers and hope you remembered to update it in every single file. Otherwise, instant inconsistency. But actually even worse than that were the integrity problems. Crucial rules, like an integrity constraint saying, say, an account balance has to be greater than 0, were just buried deep inside thousands of lines of application program code instead of being set in the database itself. Seriously, imagine being the poor programmer trying to find and fix one hard-coded rule buried on line 4,000 of some random text file. Absolute nightmare.
Thankfully, we evolved. Section 3, SQL basics, DDL versus DML.
To fix that chaos, we brought in database management systems and SQL. Now, what's really interesting about this is how SQL splits up its responsibilities into two completely distinct camps. Think of it like a construction site. On one side, you have DDL, or Data Definition Language. That's the crane building the actual structure. It creates the tables, it sets the rules. On the other side, you have DML, Data Manipulation Language. DML doesn't care about the overall structure at all. It's just the pencil writing or changing the actual data that lives inside those pre-built tables.
Okay, let's pause for a quick mid-explainer pop quiz to make sure this is actually clicking for you. Based on what we literally just talked about with structure versus data, which of these is a DDL command? Is it A, insert, B, update, C, create table, or D, delete? Take a second. Lock in your answer. All right, if you guessed C, you are absolutely correct. Create table is the DDL command because, well, it defines the structural skeleton of the database. All the other ones, insert, update, delete, those are your DML commands because they are merely manipulating the rows of data inside a structure that already exists.
And the best part is you really don't need some complex, heavy software setup to see this in action. You can practice SQL directly in a browser simulator in 3 super simple steps. Just paste your code, click Run, and read the output. For example, your DDL command create table students builds the framework. Then your DML command insert into students drops in the record for a student, say John. And finally, a simple query using a select statement with a where clause pulls that specific data right back out, instantly turning it into information right there on your screen.
Which leads us perfectly to our final stop, Section 4, Understanding Primary Keys.
Once we have these tables, how do we keep them perfectly organized for entity relationship models? And, avoid those nightmare inconsistencies of the past? Well, it all boils down to this absolute golden rule of database architecture. No two entities in an entity set are allowed to have exactly the same value for all attributes. Basically, by definition, individual entities absolutely must be distinct. Because if your database can't tell the difference between two rows, the integrity of your entire system just collapses.
So the real question is, how do we enforce that rule? We do it by using a key. In database terms, a key is simply a set of attributes that suffice to distinguish entities from each other. Let's jump back to our university example for a second. A university could easily have, 5 different students named John Smith enrolled at the exact same time, right? If we only use their names, our data would be completely hopelessly mixed up. But by assigning a totally unique student ID, which becomes our primary key, we ensure the database can perfectly identify and manage every single distinct entity, regardless of how many other attributes they happen to share. Plus, this primary key is the exact anchor we're going to need later on to use advanced SQL techniques like joins to connect this table to a bunch of other ones.
We have covered a ton of ground today, right from the basic definitions of raw data all the way up to the structural integrity enforced by SQL and primary keys. But I want to leave you with this final thought. If data is really just raw facts waiting to be queried, what undiscovered knowledge is hiding in your database right now, just waiting for the right SQL command to bring it to life? It's a pretty cool thing to think about. Keep exploring, keep querying, and we will catch you in the next explainer.